Hello, Padres. Welcome back. This week, we're going to be dealing with part 3 of our astrophysics unit. It's going to be on physics of the stars. There are going to be two things due this week. There's going to be some problems, as always, and then there's going to be the survey. Both are worth points, so please make sure you turn in both the survey and the problems. The survey, I'm giving you points, and it is important that you do it because I can't see you guys. I can't see if you have questions. I can't see how fast or how slow you're working. And so it's really helping me make sure that my pacing is good, that I'm giving you the correct amount of work. I'm not giving you too much or too little. You don't have any questions, that you're not struggling. Also, if it's, if this course material is way too easy or way too hard, it just gives me a chance to gauge how it is, because like I said, I can't see you, so I don't actually, it's hard for me to judge. So I'm using that to try to tailor the length of the lessons and the difficulty of them. So please make sure you complete those surveys. Um, all right, let's get to it. Physics of the stars. So we're going to start by defining a solar mass. A solar mass is m sub s. There's also this other funny script that you might see if you're looking online at solar masses, but we're going to be using m sub s. And it's a star's mass compared to the sun. So, for example, if I said a star has a solar mass of 1, you would know it is the exact same size as, not the same size, sorry. We're not talking about volume. We're talking about mass. So it doesn't have the same volume as the Earth necessarily. It might, but it might not. We're just talking about how much mass it has, how much material is actually there. If a star has half a solar mass, it has half the mass of our sun. And so what this does is it gives us a frame of reference to compare. If I say, a star has a mass of, 20 trillion kilograms, it's hard for us to wrap our head. Is that big? I mean, it is big, but is it bigger than the sun? Is it smaller than the sun? So this method helps us give us a frame of reference for measuring stars. All right, so we're going to look at the life cycles of several different star types. The first star type is a very low mass star. So a very low mass star is less than half the mass of our sun. So it's 0.5 solar mass. All stars start off as a nebula. So a nebula, if you recall from our first unit, is a bunch of gas and dust that's just kind of floating in space. And if there's enough gas and dust in the space, it'll have enough gravity to kind of pull itself together. And as it gets together, it's going to form what's called a protostar. So a protostar is kind of a compressed, dense nebula. It's not quite a star yet. It's just like it's like a baby star. It's like I said, it's a compressed ball, but it hasn't actually like turned on. It's not a star yet. And then what happens is it goes into what's called a brown dwarf. And a brown dwarf is it's now a solid object, but the gravity is not strong enough to fuse hydrogen into helium. And so because there's no fusion, the star is not shining. So if the gravity, the gravity is causing that pressure inside, and if the pressure is not big enough, if the gravity is not high enough, and the pressure is not big enough, we're not going to actually start fusion. So this is just because of the star is not massive enough. It doesn't have enough gravity to fuse hydrogen into helium. And because these stars do not shine, most astronomers don't classify them as stars because there's fusion is not happening. And if you recall, once again, back to our first week, my definition of a star was that it fuses hydrogen into helium. So by that definition, brown dwarfs would not be stars. However, they're too big to be planets. So they're not planets, but they're not stars. they're kind of like in this gray area. So some astronomers will call them stars, some won't. Just think of them as smaller than stars that aren't generating energy. Here is an artistic rendering of what we think brown dwarfs look like. Because they're so far away and they're not shining, we can't actually see them. But we do know they exist because the physics says so. The physics says that there are objects with this mass, and according to physics, there's not enough gravity to actually cause fusion. So they're there, but we can't see them because they're not giving off any kind of light or radiation. Okay, so this is very low mass. This is low mass. If the stars are bigger, actual stars can go down one of two paths. All stars, as I said, start off as a nebula of gas and dust. That gas and dust will compress into a protostar. Once the hydrogen fuses with helium and the star turns on, it will either become a small star or a large star, depending on how much mass is in this nebula and the mass of the protostar. So if there's a lot of mass, it'll be a large star. Small mass, obviously, will be a small star. These are called main sequence stars, the large and the small, this area right here. And main sequence just means it's kind of like the adult part of the star's life. This is the longest part of the star's life. So most of the star's life is spent here along the main sequence, this part here. And what happens, if we're up here in the small stars, actually both of them, they'll eventually run out of hydrogen. So they're fusing hydrogen into helium, which is producing a large amount of energy, and that energy's making the explosion that's the star, right? And what happens is energy that's being pushed out through the fusion process is balancing with the gravitational pull. So the fusion process is producing energy that's out, and gravity's pushing in, and it's giving the star its shape. Well, when the hydrogen runs out and the star stops fusing, gravity's still pulling it in, but there's no fusion pushing out anymore, and the star starts to collapse. And it collapses down, and it gets more dense and more dense and more dense. And when it gets more dense, it now has the ability to start fusing helium and other heavy elements. So when that starts happening, it creates much more energy than hydrogen fusing. And so we get this, it balloons out. Depending on the mass, it's either going to be a red giant or a red supergiant. And these are truly large. Our sun is going to travel along this upper path. And when our sun goes from a main sequence star here into a red giant, it's going to expand so large that it's going to encompass the Earth. It's going to swallow up Mercury. It's going to swallow up Venus. It's going to swallow up the Earth. It's going to be huge. It's going to just expand so much. So eventually it's going to run out of helium and other elements. And when that happens, it just kind of drifts off. And when it drifts off, it forms a planetary nebula up here. And what's left is a white dwarf. And a white dwarf is the core of the star that's left over. It is going to be very, very, very hot, very dense, and it's eventually going to cool off. But it's going to take millions of years to cool off because it was so hot. If we're talking about supergiants, they go through a different process. When their helium and heavier elements run out of fusion, it collapses again. And when it collapses again, it hits the core and it rebounds. So like it bounces. And when it bounces, we get a supernova. And supernovas are extremely bright. We have not seen a supernova for a long time here on Earth, but when we do see one in the Milky Way, they are like the brightest thing in the sky, and they last for a month or so, and then they slowly fade. But it's just this giant explosion, and all this energy is released, and this is where all the heavier elements on the periodic table are created, is during this intense explosion during a supernova. Picture so you guys can see. And what's left after the explosion of the supernova is either a neutron star or a black hole. A neutron star is present if it is on the small size of a supergiant. It will go to a neutron star, and a neutron star is just very, very dense. Or if it's on the larger side of a supergiant, after the supernova, it will go to a black hole. All right, so all stars start off as protostars. Start off as nebula, then they go to protostars. Then we'll either go to brown dwarfs, which would be, if we had a line up here up top, we would have brown dwarfs, or they'll go to stars on the main sequence, red giants, planetary nebula, white dwarfs, or if they're more massive yet, they'll go to large star on the main sequence, red supergiant, supernova, and then either neutron star or black hole. So let's write some of this down. So we already did less than half, which was the brown dwarf. So let's talk about between half of our sun's mass and 2.2 times our solar mass, or the sun's mass. So we said it starts as a nebula. The nebula collapses down to a protostar. Then we get a main sequence star. It fuses hydrogen into helium, releases energy. When the hydrogen runs out, the star collapses. This causes the pressure and temperature to increase, and allows the helium to fuse heavier elements like carbon and oxygen. And when this happens, this is producing much greater energy, and that's why the star balloons out into a giant. After the red giant, as the fuel runs out, the gases just drift off into space, forming a planetary nebula. And then what's left is the core. It's the white dwarf, and it's very hot, and it cools over millions of years. So this was that upper path of the previous slide, and the lower path would be high mass stars, which are 2.2 times the mass of the sun, all the way up to 315 solar masses, which is just huge. So it starts off the same, as we mentioned, nebula into protostar, into main sequence, that's the same, into a red supergiant. So the same process is happening. Hydrogen runs out, size increases, but now because gravity is even larger, because it's a bigger star, it's not just doing carbon and oxygen, but we're also getting other heavier elements, all the way up to iron. So because there's so much gravity here, we're actually able to fuse elements up to iron. And some of these are 1,000 times as large as the sun. So even though the mass, how much stuff is there, is 315 times more, the size is just 1,000 times bigger. Supernova, when it runs out of fuel, it collapses, rebounds. This produces all the other naturally occurring elements. So every element on the periodic table that is above iron occurs during a supernova, with the exception of the few elements that are produced in laboratories. We have some man-made elements that are on the periodic table, so not counting those. And then what's left at the very end, we either have a neutron star or we have a black hole. All right. Here's a video. It kind of has an Irish astronomer that goes through and talks about what I just said, talking about the life cycle of stars. Take a look. It's pretty informative. I'm not going to have you guys memorize every star in the sky. I know when I took an astronomy course when I went to a community college, and they had us memorize constellation and most of the stars up there. But there are some unique stars that we should know. The first is the largest star. The largest star in our Milky Way galaxy is a hypergiant known as VY Canis Majoris. It is found in the constellation Canis Major. It is 3 billion times bigger than the sun. 3 billion. Look at that number. Look at all those zeros. This star is huge. So that's the largest star. The brightest star is Sirius in Canis Major. So same constellation. This is the brightest star. If you look out at night, it's going to be one of the brightest that you can see. The brightest objects you're going to see at night are going to be planets. There are a few planets that are viewable right now. Venus is very, very, very bright. But if you're looking at stars, Sirius is going to be the brightest star found from Earth. Alpha Centauri is the closest star. So it's 4.3 light years away, which is very far. If we tried to send an object there, like a satellite or a spacecraft, I haven't done the math on it. I don't know how long it would take, but I would guess hundreds or thousands of years it would take to get there. It's so far away, and we're traveling so much less than the speed of light. It's a triple star system. So instead of having just one star like our sun, there's actually 3 stars, and all 3 stars are kind of circling around the center point of gravity between those 3. And we know there's at least one extrasolar planet. So there's one planet at least around that star system. So we have the largest star, the brightest star, the closest star, and there's a couple more. Polaris is the North Star, and it is in line with the Earth's polar axis, so the star does not move in the sky. So if the Earth is spinning this way, it's right up here. And so if you're here and the Earth is spinning, the sky is gonna move, right? But because it's right above the pole, that star doesn't move. And sailors used it for navigation. You can see some cool pictures too if you look at time-lapse photos or videos where they center on Polaris. You can see all the other stars are swirling around it, and you'll have Polaris that just stays stationary at the top. And this was kind of a unique star. I decided to put it on here. I don't know why. It has a name Swift J1644 plus 57. It is a star that is being eaten by a black hole, and it's in the Draco constellation. And so it was part of a binary star system, which I think is on one of the next slides. But a binary star system has 2 stars that are orbiting around a common point of gravity. And one of those is a black hole, and the other one is a star. And the star is feeding into the black hole. Or I guess the black hole's eating the star. It's eating all that material is just going into the black hole. So that's kind of a unique star. I did have someone ask during the survey about the names of stars. The names of stars came about several different ways. People have been looking at stars for thousands and thousands and thousands of years. And so some of the stars are named for different cultures, because if you think about it, we have like populations in India were around for a long time. They had names for stars. We have European names for stars. So there's different like naming systems, and some of them just kind of carried over from different places. And then some of them are stars that, like Sirius is a star that's very visible from Earth. And so that name came from some ancient culture. I don't know what language Sirius is off the top of my head. But then you have this one, which is not visible with our naked eye. And so because it's not visible by our naked eye, they give it this weird number. So if it has a number, it's not visible, and it's been designated as like has a scientific designation to it. But if it If it's visible with the naked eye, it usually has a name because some culture has named it. So this is what I was mentioning earlier. Binary stars, two stars that orbit around a common point. Most stars are either binary or higher. So that Swift star that we just mentioned, Swift J1644 plus 57, that is a binary star system with a star and a black hole. And we said Alpha Centauri, which is the closest star system, has 3 stars. Most stars have a twin or a triplet that they're rotating with. And only 15% are like our sun. So our sun is actually pretty unusual in that it's just one single star. A globular cluster is a group of stars that form a sphere or a globe. So it's just a bunch of stars kind of gathered around. Pulsars are rotating neutron stars that emit pulses of EM radiation. So remember that EM radiation is radio waves, microwaves, infrared, which is heat, visible light, ultraviolet, X-rays, and gamma rays. So our sun emits infrared because it gives off heat. We feel that. It gives off visible light because we can see the sunlight. It gives off ultraviolet because that gives us sunburns. And it also gives off, I believe it gives off some microwaves and maybe even some radio waves. So it gives off multiple parts of the EM spectrum. So just because you see that word radiation, remember it's not necessarily bad. So a neutron star that's spinning, if we're here and it's spinning this way and the pole is up and down, we're not going to be able to see that pulsar because they're actually shooting out jets of radiation along the axis. So it's shooting it up along the North Pole and the South Pole, and it's shooting off radiation along those. So if we're here and it's spinning this way, it's going to have jets that spit out this way, and we're not going to be able to see it. However, if it's spinning this way, and this is the North Pole and the South Pole's this way, we're also not going to see it pulse. But if it's spinning this way, where this is the North Pole, what's going to happen is we're going to see the light. If we're over here, we're going to see the light, and then we're not going to see the light. And then when the South Pole hits, we're going to see the light and then not see the light. And so as the poles become visible, not visible, visible, not visible, it's going to flicker. And so it looks like they're pulsing. Those are pulsars. A variable star is a star whose luminosity dims and brightens. And there are several stars, actually there's lots of stars that we know do this. Some of them are very reliable, some of them aren't. They just fade and they get brighter. And we're not talking about like something visible by the naked eye, but we can actually measure it pretty accurately and see, oh my gosh, this star is getting brighter and it's getting dimmer, and it's getting brighter and it's getting dimmer. So those are variable stars. A quasar is a massive and faraway object. It emits enormous amounts of EM radiation. We think they're black holes in the center of galaxies releasing energy from the friction from the surrounding disk. So when we have a black holes are pulling everything into it. There's a place called the event horizon, which is kind of on the edge of the black hole. So anything that's below that edge can escape, and it's forever lost in the black hole. But there are things that are outside of that event horizon that are still getting pulled into it's still getting pulled in, but it's not past that event horizon. So we can still see those objects. And if these are swirling as they're getting lowered into the black hole, if they're swirling above the event horizon, we can see that. And if they're spinning and rubbing, they're creating friction and heat, and we can actually detect those that energy. So we're detecting the energy of swirling material above the event horizon before it actually gets sucked into the black hole. So these quasars are just putting out massive amounts of energy. And we're not sure exactly what they are, but we think it's this energy, the friction of the energy surrounding the black hole. Okay. There are different star types. And it's called star spectral type. It depends on the surface temperature of the star. And I'm not sure why they came up with this system. Like, these letters don't really make sense why they're in this order. But there's a few trends I want you guys to notice. One is as it gets hotter, we're going up. As it gets hotter, we go from red, orange to yellow to white to blue. So the color is going to change. You'll notice that as we get hotter, this is the mass. The mass is getting more massive. So the more massive a star is, the hotter it gets. The radius, which is the size, once again, is getting increasing. So the more massive it is, the larger the star is. And also luminosity is the brightness. So it gets brighter. So if we have a G stars are yellow. They're around this temperature. And you can see it's about the same mass as our sun. It's about the same radius as our sun. And it's about the same brightness as our sun. So our sun is a G-class star. If you had a B-class star, you would know that that star would be much larger than our sun, hotter than our sun, bigger than our sun, and brighter. There is a way to remember this order. There's an acronym. I did not come up with this. This is well known and pretty famous, and if you're taking other astronomy classes, you'll learn about it. It is O, be a fine girl or guy, kiss me. So the mnemonic, O, be a fine girl or guy, kiss me. OBAFGKM. So let's go over a few practice questions. We're going to have our test in a few weeks. You will see some questions like this on the test. Which star is hotter, a type O or a type A? So if you think about OBA, fine. So O is higher than A, so O is hotter. Which star is smaller? So we have OBA, fine. So F is fine, girl or guy, kiss me. M is on the bottom, F is at the top. So M is definitely going to be smaller because it's at the bottom. Which star is brighter, type B or type G? O, B, A, fine, girl or guy. So B is higher than G, so B is going to be brighter. So I think you get the idea. And I already mentioned this. What type of star is our sun? Our star is a type G. So in addition to the type, there's also a subtype. So a subtype tells us not just the temperature and the size of the star. It gives us, is it a supergiant? Is it a giant? Is it a subgiant? It gives us kind of like the size. Our sun is a main sequence star, so our sun would be a G5. Okay. This is called the Hertzsprung-Russell diagram. It kind of shows the stellar evolution of stars. So you can see we have O, B, A, fine, girl or guy, kiss me. So this is hotter. This is colder. It's kind of backwards. You see 3,000 degrees is on the right and 40,000 is on the left. So stars live most of their life here along this main sequence. So it's kind of, if you're plotting the temperature versus the brightness or the luminosity, most stars for most of their life is going to be living along this curve right here. The ones that are higher up, when they run out of hydrogen, they're going to shift over this way, either into supergiants or red giants. So these are going to shift this way. These are going to shift this way. And our sun, or these green ones, are going to kind of fall over here to white dwarfs. So it kind of shows you kind of the evolution of it. Hertzsprung-Russell diagrams. You're not going to have to do much with this. I just wanted to show you this. If we were in class, what I did last year is I gave every student a different star, and you had to look up the temperature of the star, the luminosity of the star, and then we plotted them. And you can actually see that most of them were along this curve. And you can kind of see the size differences and stuff. But we're not going to do that, but you can just kind of know that Hertzsprung-Russell diagram plots the life cycle of stars. Most of them are along this main sequence. Okay. So we're going to get into a little bit of quantum mechanics and talk about the hydrogen atom. We've got a little more to go. So electrons have quantized energies. So what that means is electrons cannot have any energy they want when they're in an atom. The atom actually has like these steps, these energy levels, and you probably learned about this in chemistry, the different energy levels. N1 is the ground state, N2 is one step up, N3, and 4. And so with a hydrogen atom, an electron inside a hydrogen atom has to be on one of these levels. So if you measure the electron's energy at the ground state, all electron energies would be at 13.6 electron volts. One step up, 3.4. So they have to have those energies. So you will not find an electron inside a hydrogen atom with an energy of 2 electron volts. There's no step for that. It can't happen. So it has to be, they're quantized, or specific levels it has to be at. So for example, in the ground state, all electrons in that state must have an energy of negative 13.6. So they're all right down here. In the first excited state, they all have an energy of 3.4. There's no in-between energies. They're distinct steps. Why are they negative? The reason that these energy levels are negative is because if an electron is down here at the ground state, it requires 13.6 electron volts in order to get it to 0. And when it becomes 0, that electron is released from the hydrogen atom. It would ionize that atom. So it's negative because it takes that much energy in order to release the electron from the grasp of the electrostatic force holding the electron to the proton, right? Because they're attracted to each other. So it takes that much energy to actually pull it far enough away so it's not going to be in orbit around that proton anymore. So if you're here at n equals 3, you would need 1.5 electron volts to ionize that electron, to strip that electron. Okay. So absorption and emission. So here we have our energy levels. Photons are energy, and photons can interact with electrons. So if we have an electron, this red electron, that's down here at n equals 1, which is our ground state, and that electron gets hit by a photon, it can excite that electron, and it can jump up to a higher energy level if that higher energy level matches the energy that that photon had. So for example, let me make up some numbers here. Let's say this one is at negative 10, and this is at negative 5, this part right here at the top of the arrow. If this photon had 5 electron volts, it would cause it to jump from the 10 up to the 5. If this photon had 4 electron volts of energy, it will not kick it up to the next level because it doesn't have that energy to get it up to that level. So if the energy of the photon matches the energy of a specific level, it can excite that electron to a higher energy level. Electrons, though, don't like to be up in higher energy levels. They're unstable. So they like to go down. And when they fall down, they will emit a photon. So when the electron drops, it produces light energy. And that light energy will have the same energy as the energy lost by going down a level or 2 levels. So you can see here, this electron is dropping from n equals 5 to n equals 2. If there was 10 electron volts difference between 5 and 2, then this photon would have 10 electron volts worth of energy. Let's do some actual numbers here. So here we have an electron that falls from n equals 3 to n equals 2. So in this case, it's falling from 1.51, or from negative 1.51 to negative 3.4. So if we subtract 3.4 minus 1.51, we see it's 1.89 is the difference between N3 and N2. So that difference is the energy that that photon will have. Makes sense, yes? All right. An absorption example. So let's say an electron's at the ground state, n equals 1, which is right here, negative 13.6. It absorbs a photon, exciting it to n equals 3. What was the energy of the photon? So energy is conserved, can't be created or destroyed. So the energy to raise it from here to here, we just have to subtract these two. Even though they're negative, I just ignore the negative because it's going between this and this. So I would subtract 13.6 minus 1.5. It would take 12.1 electron volts to get it up to this n equals 3 mark. We're just adding and subtracting. It's very simple math, and that's all the math we're going to do for this week's lesson. An electron at N2 absorbs a photon, making it to N3. So if it goes from here to here, what is the energy of that photon? We just subtract those two numbers, and once again, I just make them positive just for simplification. 3.4 minus 1.5 is 1.9. Okay. So, last section, which is actually what I think is one of the coolest parts about this. The energy of a photon has a unique equation. It is h times f, which is the frequency. H is a constant. It's this constant here. And we know that frequency is related to the speed and the wavelength. We said v equals wavelength times lambda. So v is our speed of light. So we can rearrange this as c over lambda. So h is a constant. C is a constant. It's 3 times 8 times 3 times 10 to the 8. So this whole numerator is a constant. So each energy that a photon has, so if a photon is emitted, it has a specific wavelength. That wavelength corresponds to a part on the electromagnetic spectrum. So it could be red light, it could be green light, depending on what wavelength. Each wavelength has a different color. It might be not light, it might be microwaves. So whatever the energy is being released, it corresponds to a particular wavelength. So we get these things called absorption spectra. So when light passes through hydrogen gas, not all of it passes through. So you might have did this with in chemistry class. I think Dooner did it, where you have these lamps, and inside the lamp you have different gases, and you look through the little slits and you see these. So we can see these in astronomy when we're looking at stars. So the light from the star is passing through the hydrogen gas in the star, and we get these black lines. Why? Why do you think there are black lines in the spectrum? The reason we have these black lines is because these black lines correspond to the energy levels that are being absorbed by the electrons. So this is one of those states where we can't see the light because the electron took that light and went to a higher state. Each of these lines represents where the electrons are absorbing that photon, because remember, photons are light. So the energy is just passing through the gas, but those exact spots, those exact steps where it can step up, it's absorbing that photon. That photon no longer exists, which is why, because it's exciting that electron, and that's why we're getting these black marks. Each element has its own unique absorption spectra, and they're like fingerprints. So hydrogen, all hydrogen looks like this because hydrogen has unique energy levels, and those energy levels are absorbing. You can see the absorption. Helium has its own unique, lithium has its own unique, they all have their own unique spectrum. And once again, that's just because they each have their own unique energy levels, and wherever those energy levels are at, when the light goes through, it's absorbing those photons. The electrons are absorbing those photons. So we can use this to identify a star's composition. So if we have our mystery sun, we can figure out what elements are in this star by looking at the unique pattern. So if we look here, obviously our star, mystery sun, has this big black patch right here. So our mystery sun would definitely have sodium. If you look down here at the bottom, you can see these two marks here. Those are pretty unique to oxygen. So our sun has sodium in it. It also has oxygen in it. And so we can go through and we can look at all of these right here. This double band is unique to sulfur, and our mystery sun has it. So our mystery sun has sodium, sulfur, and oxygen. Excuse me. And so we can kind of use this because these are known, and we can use it to identify what elements are in our mystery sun. So this is how we know what elements are being produced in stars and what stars are. Okay. Let's say we have an absorption spectrum for a new element called fratacium. And we know fratacium looks like this. It has this unique fingerprint. But when we see it, there's space. So even though we know fratacium should look like this, we see this. It looks exactly the same, except it's shifted over to the left. So what would that mean? Remember, we're looking at light spectrums. Light is a wave. So when do we see shifts in light waves? We see it with it shifts it. So if this is our wave, and if we start moving faster, it shifts. Not faster, sorry, away from us. So if things are moving away from us, everything shifts. And so this is one of the reasons we know that we know galaxies are moving away from us is because we see the shift. And what we also see is that very distant galaxies are shifted way more than nearby galaxies. So what this means is these are moving away from us quickly. The very distant galaxies are moving away from us even quicker. So there's something accelerating, those faraway galaxies, which is why we know that dark energy exists. Because we look at this Doppler shift of the spectrum of stars. So not only do we know what elements the stars have or the galaxies have because of their spectrums, but we also know that they're receding or moving away from us quicker because we can see that they're Doppler shifted. So there are two sources of evidence for the Big Bang that we know the Big Bang exists. One is the Doppler shift of the spectral lines. It tells us everything is moving away from us. So we know it started off as this point. And as I said, we also know this is evidence for dark energy because the farther away ones are accelerating faster than the nearby ones. The other one is the cosmic microwave background radiation, which is what I talked about last week, which is the visual evidence that occurred during the Big Bang. It happened when electrons coupled to the atoms themselves, and it allowed light to freely flow. I think that's the end. That is the end. That was a long section of notes. There's a few questions for you guys to answer. I'm going to have you guys do a few of these mystery suns, so you can kind of get a feel for how to find what elements are in them. And there's also a few of the math ones. These that you'll have to do. We're not going to have to deal with this equation at all. I just wanted to show you this equation so you can realize that the photon's energy corresponds to a specific wavelength, so that you know explains why you get these those dark bands. Make sure you do the problems. Make sure you do the survey. Both are worth points. I will be around office hours Tuesday and Friday via Zoom, also Wednesday by appointment. So please come by if you have any questions. We'll talk about it some more. We'll go through some examples. Have a great day, Padres.